Who's ready for some advent of code this morning? Let's do this. Day 9 in Rust. Today's problem is called Smoke Basin. We're in a submarine and we've gone into some underwater caves. These caves seem to be lava tubes. Parts are even still volcanically active. Small hydrothermal vents release smoke into the caves that slowly settles like rain. If you can model how the smoke flows through the caves, you might be able to avoid it and be that much safer. The submarine generates a height map of the floor of the nearby caves for you, your puzzle input. Smoke flows to the lowest point in the area that it's in. For example, consider the following height map. Each number corresponds to the height of a particular location where 9 is the highest and 0 is the lowest a location can be. Your first goal is to find the low points, the locations that are lower than any of its adjacent locations. Most locations have 4 adjacent locations, up, down, left, and right, so diagonal doesn't count. Locations on the edge or corner of the map have 3 or 2 adjacent locations, respectively. And then in parentheses, diagonal locations don't count as adjacent. Good. In the above example, there are 4 low points, all highlighted. 2 are in the first row, A1 and A0. The other one is in the third row of 5. Oh, this is this A is just the article. It's not like a grid. It's not like a grid axis. And 1 is in the bottom row, also a 5. All other locations on the height map have some lower adjacent location and so are not low points. The risk level of a low point is 1 plus its height. In the above example, the risk levels of the low points are 2, 1, 6, and 6. Seems like a weird little obfuscation. Are they throwing that in there just to make sure that we're paying attention? Is this like a reading comprehension thing? The sum of the risk levels of all low points in the height map is therefore 15. Find all of the low points in your height map. What is the sum of the risk levels of all low points in your height map? Okay. All right, so this problem seems relatively straightforward. We parse the input into a two-dimensional grid, maybe a vector of vectors, or a single array with a width and a height, or a single vector with a width and a height. And then we basically just iterate over and just make sure that we're handling edges correctly. The stuff on the edges seems relatively straightforward. The question I have is are there any points whose adjacent locations or adjacent points have equal values? And if so, what do we do in those situations? The example that I'm looking at doesn't seem like that's the case just by glancing at it. So I'm not going to worry about that unless it becomes an issue. So let's go ahead and get into our parsing. Oh god, so here is our height map. And let's go ahead and plug it into our input. I like the idea of just making this one large array of chars where we know the width and height of. Let's do it like that. Get the input. We're going to split it by lines. We're going to collect them into a vector. So our height is the number of lines. And the width is going to be the first line's length. Right? Okay, so now we want to be able to read into an array. And let's just make the height I64, and it is width times height. Okay, so this just needs to be a vector. That's fine. And let's just go ahead and iterate over our lines. And start reading heights into our grid. And why don't we enumerate this? Because this will just tell us what row we've got, right? So if we enumerate this iterator, we'll get a pair of the actual value and then also the index of which line we're on. And then what we can do is we can do for column of the character in line.chars.enumerate and grid of row times width plus call equals c.parse. Actually, how do we convert basically a ASCII digit into an actual number? I think Rust has this. Or to int. So that 1 becomes 1. Okay, yes, that's what I was talking about. Parse doesn't work because parse is over a string. It's just char 2-digit. Glad that's simple. And the radix is going to be 10. So this is giving us U32s. Grid is of I64, so we can just do as I64. And that should be a very clean cast. Is that not playing ball here? Okay, this is an option. We're pretty sure that this is not. This is just going to be fine. It's complaining here because get input actually needs to be stored in a variable, or else if we don't store it, this vector is going to be pointing at a memory, like a location in memory that is dropped as soon as this expression is done evaluating. So that's why we had to store input here. Let's get it to not complain, please. Okay, all right. So it's complaining that the height isn't used yet, but I suspect we might use it eventually. Technically, we don't need it. We can also just take the length of the grid and divide it by the width, and that'll give us the height. But you know, maybe it's just useful to have that in a variable. Let me pop up the chat and just make sure it's available on my other display. I see that Arisa Snowbell is in the chat. Hello again. Thanks for stopping by. At such a weird hour too. I don't know where you are in the world, but for me it's like 10 a.m. on a Thursday. Luckily for my work, I get to set my own schedule. So in the month of December, I'm just going to do advent of code whenever I feel like it. Okie doke. So where were we in the problem? We were going to actually iterate over the grid, and we're gonna try to locate low points, right? And maybe we'll just I guess essentially just make a vector of the low points, and we really only care about their values, and we're going to add one to each value and then add them all up together, right? I think that's what it's going to be. It's hard for me to imagine that the second part of today's problem is going to resemble the first one structurally, besides the parsing, obviously. Just because this is a relatively simple thing and I don't know where this is going after this point. Okay, so what we can do is we can say for row in 0 to height, non-inclusive, and for column in 0 to width, non-inclusive. We're just going to take a look at each item and also examine its neighbors. And then we have to make sure that we account for the special cases along the edges and in the corners in particular. All right, so let's start with the upper neighbor or the north neighbor. So if the row is not equal to 0, okay, so first of all, let's actually get the value that we care about, right? Okay, this is a little bit confusing because height is the height of our grid. But height also is the value inside the height map. maybe I can just call it val from the grid. Just because it's a little bit confusing to call it the height as well. So this is row times width plus the column. Okay, so that's the value that we're comparing against. So how do we make this? What we care about is we want to make a comparison against the north one as long as we're not in the 0th row. And then we really kind of want to bail as soon as we find a neighbor that is lower, or less than or equal to the current value, right? So what we can say is if the row is not equal to 0, so we're not in the top row. We're looking at the north neighbor. Saying the upper neighbor is fine actually. Let's do upper neighbor. If we're not in the first row, we have an upper neighbor. And here what we're going to say is if val is greater than or equal to the upper neighbor's value, which is row minus 1 times width plus column. I can see the advantage of having a two-dimensional vector of vectors, just because I won't have to keep doing this like weird math here. So I think just for the sake of that, normally I wouldn't care about this, but I could see this getting a little bit inconvenient over time. So let me actually just convert this into a vector of vectors. So instead, what we will do is, this will probably change quite a bit, right? What we could do here is we could say let grid, which is a vector of I64, equal to get input lines map line. And we're going to collect over this eventually. And then for each line, what we're going to do is we're going to split this into characters. And then mapping over this, we're going to say that the character is here, and then we're going to do this 2-digit thing. 10.unwrap.collect. And let's see how that worked. It's having a hard time with this collect. Maybe it needs a type specification. Value of vec I64 cannot be built from U32. I'm missing that cast. I'm tempted to just like convert everything to U32s, just to get rid of the cast. But you know what? This is fine for now. It's fine for the time being. Okay, so our grid here is now. So our grid now. The reason why we even went through this exercise is because I think we can simplify some of this. Let's say our height now is grid.length. Basically, it's the number of rows. Let width equal grid dot. The other thing I could do is call height num rows and width num calls. Let's do it like that. Num calls is grid 0. We're just going to assume that exists, and we're also going to assume that every row has the same number of columns, which is true. So this is num rows. This is num columns. And now when we look stuff up in the grid, we'll do it like this. Okay, now we're going to look at the upper number. So if the row is not equal to 0, we're not in the top row. And the value of the upper neighbor, which is row minus 1 on the same column, and the value is greater than or equal to this, then we're not in a low point, so we can just continue here, right? We can just skip this. I think it's complaining because it doesn't like my parentheses. Yeah. Okay, now let's look at the lower neighbor. Should look like similar logic, right? If the row is not equal to num rows minus 1. This is the last row. Num rows minus 1 is the last one, right? So if we're not in the last row, and this condition here, val is greater than or equal to this row plus 1, we're going to skip. And then let's do left and right. Left neighbor. So this time we're looking at columns. The left neighbor is only in play if we have a left neighbor, and that's only the case if we're not in the first column, right? So if we're not in the first column, I actually kind of wonder if greater than 0 is a better expression here. I think it's a little bit more general. Like if we're greater than 0, we're not in the first row, right? And then for this one, it's going to be less than, and then greater than 0. And then what we're looking at is the left neighbor, which is the one whose column index is 1 less than the one we're currently on. So I think that makes sense here. And then now we're going to do the right neighbor. And this is going to look like the lower neighbor, only it's going to be num calls minus 1. And it's going to be we're looking at the right neighbor's value, which is call plus 1. And then the val here we can actually rename to height, which reflects the language of the problem. Although I do wonder if val is just simply better, because even though we're not using the word height to describe the height of the grid, width and height are language-wise potentially referring to the grid, unless maybe I call this the height map. Let's if we're going to use the language of the problem, let's just go ahead and use it. I kind of like that as all in one word, actually. Typically in like game development, that kind of thing, you have like lots of different maps. And, well, I guess they are 2 words. Like cube map is usually written as like 1 word, I feel like. Light map as well. Height map I think of as height space map. But I think this reads fine. You know what? Actually, the underscore was better. I'm going to spend all my time in this problem just kind of thinking about how to name my variables, which I've already spent most of the time doing. Okay, so we've had all these early outs, but what do we actually do once we've gotten to this point? I think what we do now is we just go to low points and we push our height, right? Because we found a low point here. So at the end of this, what we're trying to do is we're going to print out reading the problem again. We're going to print out the risk level, the sum of the risk level of all the low points. So we found all the low points. The sum of the risk level is pretty easy to do, but then what is the risk level? The risk level of a low point is 1 plus its height. All right. So if we were to like explicitly do this, we could map over each low point and then add 1 and then sum them all up. We could also just sum them all up and add the number of items in the list because they're each worth 1. But I'd rather the code, because we're not really like worried about optimization here, the code maybe should just reflect the language of the problem more explicitly, right? So let's do low points.map. It's got a height. Now we've got the risk level and we add 1 to it, and then we're going to sum these together. And I think I need to actually convert this to an iterator first. Is it complaining? Sum I64. I would assume that it would just know what to do here, but it doesn't. But you know what? That's okay. And we've got one warning here. For some reason, the autocomplete added this thing in here that we don't actually need. It's being a little bit aggressive there. And let's go ahead and run this. We've got 496. Plug that in there. And we got it right. It's this year has been interesting in that, like, I haven't really, like, generally, I would say, like, maybe 1 out of 3 times when I do this in the past, I can get it right on the first answer. And that's just because when I do it in Rust has such a strict type checker and borrow checker and everything like that, that it kind of, like, finds a lot of my stupid mistakes. But this year has been different in that, like, I think there's probably been only one other problem that I've worked on that I got it right on the first answer. Part of it is just that this is the first time I'm streaming and I'm trying to like think about programming while I'm talking at the same time, and it's a different experience. And it's also just like, you know, every year is possibly just a little bit different. There's a little bit of variance, right? All right, so now that we've got that down, let's just go ahead and commit this to Git so that we have a clean slate going into part 2. I'm going to copy over my code from part 1 into part 2. And then there's just a little bit of finagling in part 2 that I want to do just to get it nice and clean. That should do it. It compiles, it runs. Just going to reload the editor real quick just to make sure that language services will recognize the new directory. And we'll go ahead and focus on part B, which we don't even know what it is yet. Let's take a look. Okay, so part 2, you need to find the largest basins so you know what areas are most important to avoid. A basin is all locations that eventually flow downward to a single low point. Therefore, every low point has a basin, although some basins are very small. Locations of height 9 do not count as being in any basin. I think 9 is the highest height, right? And all other locations will always be part of exactly one basin. The size of a basin is the number of locations within the basin, including the low point. The example above has 4 basins. The top left basin, size 3. So the 9 doesn't count. The top right basin, size 9. The middle basin, size 14. The bottom right basin, size 9. Find the 3 largest basins and multiply their sizes together. In the above example, this is 9 times 14 times 9 equals 1,134. What do you get if you multiply together the sizes of the three largest basins? Okay, so this is like an interesting curveball where not only are we trying to find all the basins, we're trying to find the sizes of them as well, and then also just make sure we remember the sizes up to the point where we compare them all to each other. Okay. So it seems like the input is designed such that, like, essentially what we're doing is what looks to be a flood fill algorithm, right? So flood fill, like if you're using a paint program, is where you have some notion of there being a barrier, and in a paint program, it's like either like non-transparent colors or just like maybe some kind of continuous line of color discontinuity, right? If you don't have a transparent color. And then what you do is you essentially do a little bit of like a search, right? You start from the point that you click on in a flood fill, and then you basically incrementally look outwards, however your units or cells are connected. And in this case, we're just connected to our adjacent neighbors. And we're just going to basically recursively or iteratively expand from those until we hit the number 9. And we also want to make sure that while we're iterating and doing this search, that we are not double counting anything, right? And I think the way that we do that is maybe that we only ever look at... Well, let's actually, before I get too specific about it, maybe we can come up with an example and then see if we can come up with like an example algorithm, and then come up and try to see what the edge cases are and whether there are opportunities for double counting that we need to be aware of. I am going to take a quick bathroom break, and I will be right back. All right, everybody. Thanks for waiting. I'm back. Where I left off, I was talking about how to implement a search algorithm from our lowest points. I can already tell that, like, I think I was talking about, like, you know, how much of the previous part's solution we can continue to use in the second part. And I think maybe a bit, right? Like, what we actually need to know for a low point is its location and its height. Although we technically don't need to like remember its height, because we can just look it up pretty trivially from the height map. right? So what we actually need to do is just remember where the low points are and push them into a list. So maybe what I can do instead here is actually just accumulate a list of low points, which are going to be, it's going to be a tuple of usize, and these are going to be x and y coordinates. I actually don't know if I want to call this x and y or if I want to call this row and column. Maybe it's better because when we look up things in the height map, we're looking up things in terms of row first and then column, that our low point list stores this data in row column order. The other way I could do this is I could make a structure, which is a little bit of extra code, but I think it's a little bit more clear when we actually have to specify the name of a property of a structure and calling it row or column, just so we're not confused about ordering. So that's what I'll do here. Let's call it a point, or a location. Let's call it a point. And then we have a row, which is a usize. It's an index into a grid, or index into a vector, and then there's a column, which is also usize, also an index. And let's make this vector a vector of points. And then what we're going to push is a point with the row and column that we're currently on. And then maybe what we can do instead is let's just debug print the low points. It's not going to change the nature of our program right now. Oh, I need to derive. If I'd use a tuple, I wouldn't have to do all this extra kind of Rust boilerplate. But honestly, this isn't that bad. And I think we may be able to prevent some silly mistakes if we're able to be super explicit about the rows and columns. Sometimes I think when it's X and Y, that is familiar enough to the brain that I'll just use a tuple for that type of thing. And even in this case, maybe a tuple would have been fine. Maybe I would not have run the risk in a program this small of confusing the two, but you never know. It's very easy for me to do make really silly programming mistakes. That's just who I am. One walking programming mistake. All right. So enough about that. Let's talk a little bit about flood fill algorithms or search algorithms in general and see what we can come up with. Just taking a couple of these examples, I'll just paste them into a new buffer and we can play around with them. What's a little bit tricky about this is I can't highlight anything. So I can see why doing this in HTML would actually be really nice. I can't tell if this is just a visual effect, but it almost looks like in this, can I zoom in here? In this rendering, it almost feels like we're getting a little bit of bloom or haloing around these characters. And it makes me wonder what's going on here in the actual HTML or CSS. So this is what I'm spending my time doing here, is looking at the HTML of the Advent of Code webpage. I'm looking at this character 0, and it's interesting to me that the emphasis is going on here. I wonder, there's probably a lot going on here that I don't actually appreciate the significance of. How is this halo happening? Is it JavaScript? Is it adding another character, overlaying another character at exactly the same point, and then blurring it? What's going on here? 43210. Okay. That's bold. And then what is the style on this? It's not calling out the character 0 in the markup itself. So that makes me wonder if there's something happening in the JavaScript to actually add that extra halo effect. That may be something to ask Dom about. He's a CSS expert, because it makes me really curious. I'll probably check in with him a little bit later. Maybe Dom and I want to do a problem for Advent of Code over the weekend together on the stream, and maybe we can talk about it at that point. I'll have to make a note of that. Anyways, I feel like I'm procrastinating now on solving the problem, but it's more that I'm just trying to figure out a way to communicate about the problem in a text file where I don't have to bold anything. So I've just copied these two examples are a little bit, I think, easier to talk about just because the low points are in the corners. It's this 2 in the upper left and the 0 in the upper right. And then we can just basically see how we can come up with an algorithm to sort of move towards the 9s. Okay, so a general algorithm might be to... I'd say one of the straightforward ways we can do this is we sort of have the notion of just doing a search, right? And we can, like, the search is technically exclusive, right? Recursive, where if we want to search a particular, like, cell on the grid or a point in the map, we can just look in all 4 directions, up, down, left, right, and see if we encounter any number that is just not 9, right? Or actually a number that is greater than or equal to the current number that we're on, but is not 9. We're not in a basin if we get to another neighbor where it kind of like dips down again. I think that's the case. Although I don't know. I don't know if that actually is possible in this formulation of the problem, because the basins are all mutually distinct. And if we had a case where, let's say, the highest point was 7 and 2 basins kind of like meet at that 7 would be double counted. Like, and there's nothing in the rule set of this problem that allows us to differentiate between those 2 different basins. So I feel like this problem is just going to reduce down to finding which locations have the height of 9 in. So what we can do is, in any given point that we're searching, we can look in all 4 cardinal directions, see if we hit a 9, and if not, add that cardinal direction into the bucket of things we want to search, right? And then we pull that thing off the list, and I don't think it matters whether we do this in a depth first or breadth first styles, so we can use a queue or a stack. It doesn't really matter. The thing that we do want to make sure is that in either of these cases, we're not double counting any locations. We can avoid double counting by making sure we obey a particular rule in terms of like how we step through the map. But an easier way to prevent double counting is to just create a blacklist, or I think deny list is the better language these days. So we create a deny list, and what that means is, like, every time we search a cell, the first like iteration that gets to a particular location in the search, or basically as we pull something off the list, we add it into a deny list. And then before we add something onto a list, we check to see if it's already in the deny list. And if it is, then we shouldn't search it because it's already in the list, right? Or it's already been processed. So I think that's actually probably it's going to turn out to be simpler code that way. So we want to find our basins. And what we care about in our basins is really just the size of the basins, right? So like at the very end of this, what do you get if you multiply together the sizes of the 3 largest basins, right? So let's just create a list of basin sizes, right? And this is just gonna be a vector of, I guess it's just, it doesn't really matter. It's just an integer that we're adding up. And we'll construct the vector. And then for each one of our low points, we're just going to conduct this search, right? So the search code is going to go inside this for loop. And at the end of this for loop, we're going to basically push the size of this low points basin in there. And at the very end, what we're going to do is we're going to sort these basin sizes by their size, get the largest 3, and then just multiply those 3 values together. So not too bad. The search is where it gets a little bit complicated. So I think I'm just going to do a stack here. I'm just going to do depth first search. Stacks are maybe a little bit easier to work with. If I wanted to do a breadth first search, I'm actually kind of wondering if mechanically the depth first search or the breadth first search is going to be better. Maybe I want breadth first search. So I think in this case, I'm going to use a data structure that is going to be first in, first out, rather than last in, first out. And so that means you need to basically be able to push on a list and keep pushing things into the back of it, but then take things off the front of it. I think probably a vector would be fine, but like Rust has a double-ended queue that we can use for this exact use case. So we're going to say let the queue, I'm just going to use the letter Q, equal is a vector double-ended queue of points, right? And how do I make a double-ended queue that I just add something to immediately? I'm not going to worry about that. We're just going to push onto this pushback. We're going to push onto the back and pop off the front. It doesn't really matter which direction you go. I think the data structure is designed to allow you to do both things. We're going to start with the initial point. And consider dereferencing the borrow. Isn't this copy? It should be fine. Oh, you know what? It's a borrow in this. Can I add a dereference here? It doesn't look like I can. So I'll dereference the borrow here. We're just pushing there. The queue needs to be mutable. And then we're also going to make a deny list. So what do we want to call that? We'll call it already done or processed. Let's call it done. And let's just make this a hash set of points. And I realize I think we're going to need to make this hashable. And in order to do that, this needs to have partial equal, and also it needs to be hashable. Okay. And so that's a hash set of points. We're just going to create this hash set dot new hash set : new. Working in too many different languages these days, I get confused. And then we're going to call done in this as well. I'm gonna add the point to done as well. It's when I say done, what I mean is that it has been added into the list. So maybe process is a better word, because we're not technically done with it yet. We still need to search it. Maybe added to queue already in queued. Yep. And the reason why this is not the same thing as the queue itself is that we're going to be like removing this point eventually, but our search will revisit it at some point, and we want to make sure that we don't. Already in queued, insert the point. Okay, so we're just gonna go until the queue is empty, right? While queue.length is greater than 0. I think already in queued is just the size of this set is going to be the size of our basin, right? Because we're basically going to visit everything that is part of the basin as part of this. So really what we could call this is basin points, right? Okay, so we just need to look at the points above, below, and to the left and right, and make sure that they are not the value 9, and if not, we add them to the queue and to the basin points. All right, so let's take a look at this. Okay, so if it's gonna be a structure very similar to this, right? So if point.row is greater than 0 and we're just going to break out some values here just to make it easy to type. The height of our current value. We don't really actually care about the height. We just want to make sure that the thing that we're visiting, its height is not equal to 9, right? So the height of this thing is not equal to 9. Then we want to add this to the queue, but only if it's not already in basin points. I wonder if a function here would help us, because we're going to be doing a lot of repetitious processing here. The other thing we can do is actually push these onto a list, right? So let's actually do that. So let's say that we have a, let's just call it the neighbors, which is a vector of points. And this is equal to vec new, and the upper neighbor is basically if our p row, if we're basically on the second row of our current point, and then we don't need these anymore. What we'll do here is just add this to the neighbors. Neighbors dot push point. We're going to use row is row -1, and then our column is p.call. And this is where maybe actually having the row and column available is just going to make the code a little bit more concise. Row -1, and then call we don't even need to specify anymore, because the name of the property is the same as the name of the variable, right? What are you complaining about here? Unexpected token if it's because I'm missing semicolons. Okay, so where was I going with this? We're essentially going to be, do I have num rows available globally? I do. That's great. We're going to be just repeating this stuff for the neighbors. The lower neighbor is going to be row +1. And we're going to repeat this for left and right, right? Get rid of this extra condition. The left neighbor is column -1. And the right neighbor is column +1. Okay, so now that we've gone through this, process, we want to filter these out, right? Neighbors is equal to neighbors dot filter, well, iterate, filter, and this is a point. And the point can't be already in our basin points. Basin points dot contains. Do I want to use p again? I want to use maybe n for neighbor here, because I'm already using p. So we want to filter anything that doesn't have the, and we want to filter any neighbor that is already in the list of basin points, because it means we've already processed it. And we want to make sure that its height isn't 9. This is the thing that we were worried about in the first place, right? So if we go to height map, n dot row and dot column is not equal to 9. And then we will collect this into a vector. It's having a hard time with this. Vec point cannot be, okay, so we just need to map this into, can we just do cloned? And neighbors, it's never read. That's fine. Okay, so what we've done is we've basically removed the neighbors of the current point that we've already looked at, or if they're basically, I typed 0 here. If they're basically the barrier for our search, which is anything with a height of 9. So now that we're here, we actually want to add the neighbor to the queue. And we want to add the basin points to, we just want to add this, we want to insert this into the basin points. Yeah. Oh, okay. And then I realized that P here, we're going through all of our low points. I think what we actually want to do here, this is actually a little bit of a mistake that I've made here. What I want to do here is for all of these, I actually want this queue. I want these to actually live outside of this loop. Oh no, wait, these are all the low points. So they're going to have mutually exclusive basins. What am I thinking? What I do need to do though is somehow, I don't care about P here anymore. I actually what I want to do is get the next thing off of, get the next low point, or get the next item out of the queue. So I need a name for this. It's the thing that we're currently searching, or the thing that we're currently processing. A lot of times I just like to use the letter I for these because I is typically like an iterator variable, but I don't love that. I'll just call it current, right? Like cur equals q dot push or pop front, right? We're just pulling out the front. And then now what we care about is this is q dot row and q dot column. Okay. Pop front unwrap. And this is cur dot row, cur dot column. Kind of just talking and typing nonsense right now. Row minus 1, row plus 1, call minus 1, call plus 1. I was just sanity checking that I was using the right variables in the right places. We're pushing. Oh, n doesn't exist because what we really care about is we actually need to do this in a loop over the neighbors, right? For n in neighbors. And I don't even know if we need to do a dot iter here. Normally we have to do a dot iter because we're doing references, but we don't really need neighbors once we're done processing it. And I actually do wonder if maybe instead of saving the temporary here, we could just do a for each. And not worry about the clone here. Just let this happen. And I think I need a dereference here. Can I borrow basin points? Oh, because is it because I've already borrowed it here? All right, I actually think rather than do this like kind of like dot chaining nonsense, it might be easier if I just iterate over the neighbors for n in neighbors. Just do a regular for loop. And then for this, I'm going to reverse this. If the basin points list already contains the neighbor, we don't need to worry about it. Or if the height map is 9, we've reached the end of our basin at this point, we're just going to continue. We're going to go to the next neighbor. Otherwise, we're going to do this push. And I think I like this a little bit better. It's totally straightforward. And this needs to be borrowed. That's the way that sets work. Okay, so now this should extend our queue, maybe, and we'll process the whole queue here. And then basin points is essentially going to give us the size of the basin. So once we're done with this while loop, once we're done with our search, we're just going to say that our basin sizes, we're going to add on to the end the size of basin points, the length of it. Expected I64, it got U size. Okay, that's fine. I just sort of didn't declare it correctly. Basin sizes, this is a U size. Makes sense. Now, and then this is not mutable, I'm guessing. Yeah. Okay, now that we've got that, we want to sort them. And then we want to just get the last three. Or maybe we should just do the first three. Can I reverse these? If I reverse them, is this an iterator or is it just reverses the order in place? Okay, that's perfect. That's what we wanted. So what we can do now is we can print out the top three, or just the product of the top three, right? Basin size is 0, basin size is 1, basin size is 2. Got a problem in here. Oh, it imported extra stuff that I didn't need. And I'm just going to run and see what happens. If it does an infinite loop, I'm already super happy. It did give us some kind of answer that I'll just plug in and see. We might have gotten it right. Oh, we did. That's great. So we got lucky on this problem where I think both times I tried an answer, I got it right. I consider that much more a product of luck rather than skill at this point. But hopefully the structure of this program makes some degree of sense. The search piece of this is, I think, the interesting thing. We're essentially just doing a breadth first search with some amount of deduplication, which is this one here. All right, well, that was Advent of Code Day 9. I think this one was a little bit simpler than yesterday's, or at least simpler for me, just because I had the context for this problem. And it didn't require as much kind of like nitty-gritty logical analysis. This is really, I think, more of a classic algorithms problem. Okie doke. Well, we will see everybody tomorrow for day 10. Take care.